I'm just going to mention these special factoring patterns for a minute. We'll talk more about it when I come back on Tuesday. But sometimes they are a little bit quicker than factoring the normal way, especially with the difference of two squares. Real quick, I'm just going to show you how this works. So if you have two things that are perfect squares, so in this case a squared minus b squared in the pattern, maybe it helps in the example. If you're asked to factor, for example, x squared minus 4, typically, and you're still allowed to think this way, you could think of two numbers that multiply to negative 4 and add to 0, right? Because it's missing that b term. So that b must be 0. Those two numbers, lo and behold, are 2 and negative 2. So factoring old school still works here. Okay, so unfoiling is normal still. If you want to use the pattern, how the pattern works, maybe I'll show you down here with the x squared minus 49. If I want to match this to that difference of two squares pattern, I need something squared, which I have, x is being squared, minus something squared. 49 is 7 squared. So now it fits that pattern perfectly. So obviously, a in the pattern matches with x, and b in the pattern matches with 7. So this would factor as x plus 7, x minus 7. That's all the pattern's doing. The second pattern, a perfect square trinomial, here's with a sum. Obviously, d's being squared first. We can use the same concept as the 49 in the previous example and know that 6 squared is 36. And then it's kind of obvious to see the center here. The plus 2ab shows up as 2. A was d for us. B is 6 for us in this case in the pattern. And 2 times 6 is 12, so I know this will factor as d plus 6 squared. Okay, but you don't have to use the pattern. I'll show you in C. You can get away without using the pattern. So C, it fits this third pattern, this third perfect square trinomial pattern. But let's do it without the pattern. So without the pattern, I'd see 169 and negative 26. And I'd know that I need to pick two numbers that multiply to 169 and add to negative 26. So these two numbers, just like before, have to multiply to 169, and they have to add to negative 26. So those numbers, negative 13 and negative 13, are those winners. So z minus 13 and z minus 13, or, as we all know from vertex form, that's the same thing as z minus 13 squared. So whether you use the pattern or not is up to you. I show them to you. I'll show you them again later on. But you can get away with factoring without using them. The most important part is the solving by factoring. We haven't seen any quadratic equations yet. We've graphed quadratic functions. For example, we've graphed things that look like this. But we haven't solved them. We saw on Friday in the shark bait, though, that we can find their solutions on a graph. So if I had a graph of this might even be the actual shark bait question. But if I graphed this quadratic, it would look something like this. And wherever it crossed the x-axis, those were our roots, was one name for them. Zeros was another name for them. Now we'll often call them solutions. So we could have found them before with a graph. Now we're going to find them by factoring. And if you can factor a quadratic, this is the easiest way to find those solutions where it crosses the x-axis. And even if you struggle a little bit with factoring, it's just so fast. Once you get it, once you grasp the concept, it's just so fast to factor. How we'll solve it from that point is even easier. So the zero product property, this just says if two things multiply to 0. So if the product here specifically of two expressions is 0, then one or both of those expressions had to be 0. That's common sense. We know that to multiply to 0, one of the things has to be 0. What's great about this is if you get a quadratic equal to 0 and factor it, for example right here, if I have x plus 5 times x plus 2 and that product is 0, that means either x plus 5 has to be 0, right? Because 0 times x plus 2 would be 0, or x plus 2 had to be 0 in order to get that product of 0. That gives us two baby linear equations to solve, and we can all solve these baby linear equations. Okay, so this will be key to solving these quadratics. So even though they're bigger, even though they're scarier, we're going to solve them. Oh, my eraser's not working. It's okay. But we're going to solve them just like little linear equations after we factor. So let's take a look at this example. What are the roots of the equation x squared minus 5x minus 36 equals 0? So there's that word roots. Just means solve. And for now, we're going to solve by factoring. So if I factor x squared minus 5x minus 36 equals 0. Equals 0 is very important. It's the only way I can use that zero product property. And the factoring part's the same. So for now, I know x and x comes first. It's the only way to get x squared. So it's the only way to get x squared is x times x. Now I just need to think about two numbers that multiply to negative 36 and that add to negative 5. So I know if they multiply to a negative, they have to be opposite. They're adding to a negative, so I'm thinking the bigger one has to have the minus with it. And those two winners that I'm thinking about are negative 9 and positive 4. And I can check this. Negative 9 times 4. Yes, that's negative 36. Negative 9 plus 4. Yes, that's negative 5. So these are my winners and my factors. And now I'm not done. I have an equation now. I actually have to solve. But what this zero product property says is that because those two factors multiply to 0, that means either x minus 9 has to be 0 or x plus 4 has to be 0. And these are super easy basic linear equations. I just add 9 to both sides in this one and I get x equals 9. Right? 0 plus 9. I don't know if I can squeeze the little plus 9 under here. So I get x equals 9. Here I subtract the 4 from both sides. I get x equals negative 4. So my solutions, not my winners to my factors, were negative 9 and positive 4. But my actual solutions, when I set them equal to 0, are positive 9 and negative 4, which in this multiple choice is option C. I mean, it's that easy, so it's just factoring with a little extra step involved.